Welcome to today's Explainer. We're breaking down the definitive guide to moving way beyond those basic AI interactions. We're drawing directly from AI expert Aishwarya Srinivasan's phenomenal breakdown on large language model fine-tuning. Because let's be real, everyone in the tech world is talking about fine-tuning right now. But the harsh reality? Most teams are burning thousands of dollars doing it completely wrong. So if you want to know what it actually takes to build production-level, customized AI, and not just ping an endpoint, you're in exactly the right place. Let's get into it.
Aishwarya Srinivasan sums up the current landscape perfectly. She notes, many people would have made a fine-tuning API call, but when you ask what's actually happening under the hood, the answers get fuzzy very fast. And she hit the nail right on the head. Fine-tuning has aggressively positioned itself as one of the most highly requested skills for AI engineers today. And yet it's still deeply misunderstood at a fundamental level. There's this massive gap between running a simple tutorial script and actually engineering a custom model. So we're going to clear up that fuzziness right now.
Okay, let's dive into this roadmap for today. First, beyond the API call. Second, open versus closed weights. Third, the fine-tuning toolkit. Fourth, your fine-tuning roadmap. And fifth, data quality and evaluation.
Section 1. Beyond the API call. Understanding the shift in scale. To really grasp fine-tuning, we kind of have to understand how the entire chronological evolution of machine learning has totally shifted under our feet. Years ago, in traditional machine learning, a company owned the entire pipeline. You gathered data, you built a model, and you trained it entirely from scratch. But today, with large language models, the paradigm has shifted. Massive foundational labs like OpenAI and Meta handle the pre-training phase. Think of pre-training like teaching a child the entire English language and fundamental logic. It takes massive GPU clusters, months of compute, and literally trillions of tokens of data. As an AI builder today, you don't do that. You operate in the post-training phase, using a model as a service. Post-training is like sending that articulate adult to medical school to learn a highly specific trade. You're taking a model that already knows how to speak and reason, and you just adapt it to your specific use case. So why can't you just train it like the old days? Well, it all comes down to sheer scale. Back in traditional ML, we were updating hundreds of thousands, maybe a few million parameters. Fast forward to today, and LLMs range from billions to over 1 trillion parameters. You literally cannot casually update 1 trillion parameters on your local GPU. The math doesn't just break, it completely shatters. Attempting to do that would cost millions of dollars in cloud computing fees. So that massive shift in scale sets the exact stage for why we absolutely require specialized, highly efficient fine-tuning methods. Section 2, open versus closed weights. The rules of the road. Before you jump into any AI project, you absolutely have to know what kind of model you're allowed to touch. You basically have two paths here. First, open weights models like Llama or Mistral. You can download these, access the underlying weights, and tune them right on your own infrastructure, total granular control. Then you've got closed weights models like GPT-4 or Claude. You get zero access to their weights. If you want to tune a closed model, you have to use their native provider API. It's a complete black box. You send them data, they do the compute, and you get a tuned model back without ever seeing under the hood. Why does this matter? Well, imagine you're handling highly sensitive, regulated enterprise data. Sending it into a closed black box is a huge compliance nightmare, which is exactly why open weights fine-tuning is becoming undeniably crucial for enterprise teams.
Section 3, the fine-tuning toolkit. PEFT, full fine-tuning in RLHF. Now, what's really interesting about this slide is how we actually solve that massive compute problem. Keep this specific number in your head, 100 million. When you're looking at a 70 billion parameter model, you don't actually need to update every single parameter just to make it better at a specific task. Enter PEFT, or parameter-efficient fine-tuning. Techniques like LoRA allow you to freeze the original massive model weights and instead just inject tiny trainable matrices into specific layers. Think of the frozen 70 billion parameter model as a gigantic, priceless encyclopedia. You definitely don't want to cross out words and rewrite the original pages. That's destructive, it takes forever, and it's super risky. Instead, LoRA is like sliding a transparent sheet of plastic over the pages and just adding a few highly specific sticky notes. You get the specialized knowledge without altering the massive original book. So instead of updating 70 billion parameters, you're essentially training just about 100 million. It is a massive, game-changing reduction in compute and cost.
And the toolkit gets even cooler. QLoRA, or quantized low-rank adaptation, takes this a step further. It freezes the base model to 4-bit precision and then runs LoRA on top of it. Basically, quantization compresses the model's memory footprint by rounding off overly precise decimals.
What this means in plain English is that you can actually fine-tune a massive 70 billion parameter model on one single H100 GPU. Because it dramatically reduces memory while maintaining performance, QLoRA takes fine-tuning out of the hands of billionaires and puts it right into the hands of a solo developer in their bedroom. It's truly the default starting point today.
Let's synthesize these methods so you know exactly when to use them. QLoRA has a beautifully low compute cost and is perfect for adapting a model to your specific domain or tone. Say you want your AI to answer questions specifically from your proprietary HR handbook, QLoRA is your go-to. Full fine-tuning, on the other hand, updates every single parameter. It gives you maximum flexibility and deep customization, but the compute cost is very high. It's expensive and slow. If you're forcing the model to learn fundamental new reasoning pathways, you have to bite the bullet and do a full tune. And finally, we have RLHF and DPO, which have high compute costs, but are specifically designed for aligning a model to human preferences.
Let's actually zoom in on those reinforcement flavors, because this specific space has completely exploded recently. First, verifiable rewards. This is brilliant for math or coding because the model auto-verifies its output with absolutely no expensive human labelers needed. Second is classic RLHF, which uses the PPO algorithm and trains a separate reward model based on human preference. Powerful, but super expensive. Finally, we have DPO, direct preference optimization. DPO is a massive industry shift right now. Training a reward model in RLHF is basically like hiring an expensive consultant just to tell your AI if it did a good job. DPO cuts out that middleman entirely, skipping the reward model for a single step tune. It makes the whole process drastically cheaper and faster, which is why it's the new default for open source preference tuning.
Section 4, your fine-tuning roadmap, the strategic decision tree. Let's move to and see how this builds.
Here is the ultimate strategic decision tree for developers. Step 1, optimize prompts and context. Literally, do not start by fine-tuning. People spend 10 grand tuning a model, only to realize a well-crafted prompt with a 5-shot example would have done the exact same thing for pennies. Always exhaust your prompting options to build a baseline first. Step 2, when you're ready to tune, use QLoRA for domain adaptation. Start small and efficient. Step 3, full fine-tuning, but only if QLoRA completely fails to meet your quality bar. And finally, step 4, layer on RLHF or DPO only when you specifically care about aligning the model's style and tone to human preferences.
Section 5, data quality and evaluation, the guardrails of fine-tuning.
So, the crucial point is this. All those fancy techniques mean absolutely nothing if you ignore this golden rule. Garbage in, garbage out. Fine-tuning with a bad dataset on a good model makes the model bad, not better. Data quality is consistently the biggest bottleneck across all these methods. You're directly teaching the model how to behave. If you fine-tune an incredibly smart base model on thousands of toxic internet comments, you haven't made a smarter AI, you've just created a highly optimized internet troll. The model learns exactly what you show it, for sure. Which brings us to this. If you don't have a clear evaluation metric and a clean eval set before you start, did your fine-tuning actually improve anything? Or did you just spend thousands of dollars on compute to make a model different, but not necessarily better? You have to ask yourself that every single time. Before you write a single line of code, define your metrics. Thank you so much for joining this explainer on the strategic roadmap of LLM fine-tuning. Rethink your evaluation strategies, lock in those baselines, and start building smarter. See you next time.